Hey guys, welcome back to another maths video, and in this video I'm going to be showing you guys how we can prove the derivative of ln x from first principles. So if you don't already know, the derivative of the natural log of x is 1 over x, and this is a pretty cool discovery because what it shows is the integral of 1 over x, if we have the graph, integral, let's just say from 1 to infinity, so this area here, you might think that this is finite, but it's actually not, because this area is equal to ln, well, it's going to be ln infinity minus ln 1, which we know is 0. So this area is going to be ln of infinity, and ln of x doesn't actually converge, it's an unbounded sequence, so it goes on forever, which means this area is also infinite. Like that. That's a pretty cool fact. And yeah, let's just look at how we can prove this from first principles. So we know that the definition of the derivative from first principles is the limit as h goes to 0 of f of x plus h minus f of x over h. And this basically just comes from the fact that if you take a gradient triangle with the points x, f of x, and x plus h, f of x plus h, then this width is going to be h, this height is going to be f of x plus h minus f of x. So the gradient at this point is going to be the rise over step, or f of x plus h minus f of x over h. And then the derivative is basically the instantaneous rate of change. So as h goes to 0, that's how we get a derivative. So that's where that definition comes in. Now we can use this definition, I'm going to make this green, to prove the derivative of ln x. So let's say f of x is ln x. That means the derivative of ln x, I'm going to write it as this, is equal to the limit as h goes to 0 of ln x plus h minus ln of x all over h. And yeah, this is just going to require a bit of algebraic manipulation. So firstly, I'm going to move this 1 over h out to the start, and then you can see that this ln, we can use our log laws, so we can rewrite this as ln x plus h over x. And we can then use another log law. So what I'll do is simplify this in a bit into just become 1 plus h over x. Hopefully you can see how that works. We just split the fraction. And then I'm going to use another log law to move this inside of this into the power. So this is going to now become ln of 1 plus h over x to the power of 1 over h, like so. Okay, there we go. Now, what I need to do is make a substitution. So before we make the substitution, what we need to know is the number e it's pretty common. It's got a number of definitions. For example, one definition might be the derivative of the function e to the x is itself. You can define it based on that, since it's the only function which has that property. You can also define it with its Taylor series. I believe it's x over r, like that. That's also a definition. But the definition of e which we'll use today is the compound interest definition, which is essentially the limit as use u in this example. And okay, yeah, limit as u goes to 0 of 1 plus 1 over x to, sorry, not as u goes to 0, as u goes to infinity. That's what I was doing wrong. And I'm trying to remember if that's right. Something seems wrong about it. Let me think. No, I think that's correct. I think not x there, should be a u there, but I think that's correct. Okay, so this is the definition of e. Now what we can do is let's make a substitution here. So I'm going to let's use a as our variable. A is going to be 1 over h. So we can now transform this limit into well, as h goes to 0, a is going to go to infinity, specifically as h goes to 0 plus, because we're approaching it from the front. So that's what we're going to use. We're going to say the limit as a goes to infinity of ln 1 plus, well, h over x, if we write it in terms of a, well, h can be same thing as 1 over a to the x. So, yeah, we're going to write it as 1 over a multiplied by 1 over x, like so. And, okay, now I need to move this down a little bit. So we can write this h over x as simply 1 over a multiplied by 1 over x to the power of 1 over h. Well, as h goes to 0, a is going to go to infinity. So 1 over h is simply just a. All right. And from here, oh, sorry, I see my mistake. Sorry, guys. This was the substitution we meant to make. A is equal to x over h. Okay, there we go. That makes so much sense. So obviously, same sort of thing. X is just a constant. So as h goes to 0 plus a still goes to infinity. But now what I can do is we can just write h over x is just 1 over a. And 1 over h is the same thing as a over x. All right, there we go. So now I can put this transformation in properly. 1 plus 1 over a. And we're going to use an exponent law here. So if we have 1 plus 1 over a to the power of a over x, we can write a over x as 1 over x multiplied by a. And an exponent law you should know is that a to the bc is the same thing as a to the b to the c, which is the same thing as a to the c to the b. So what I can do is write 1 over a to the a over x as 1 over a multiplied by, to the power of a to the power of 1 over x. There we go. And now I can move this limit, I can evaluate this limit as a goes to infinity within the ln, because ln is a continuous function. So what I'm going to do is first take this out into the front, and then we can move the limit inside of ln because ln is a continuous function. So that's going to be 1 over x multiplied by ln lim a goes to infinity of 1 plus 1 over a to the a. And here's where our definition of e comes in. As you can see, u is just a dummy variable, so we could always just replace a with u. And then therefore that's equal to 1 over x multiplied by ln of e. By definition, ln of e is simply just going to be 1. So therefore, that's how we get the answer. The derivative of ln x is equal to 1 over x. So yeah, that was how we got there. Hopefully you guys enjoyed this short proof, going through a lot of definitions and interesting facts. And yeah, see you guys in a future tutorial. Bye.